Hi everyone, welcome back. This will be the last of the MATC58 lectures. On Thursday we will of course be having in-class presentations instead. So for the very last lecture I thought we'd come full circle and talk about some epidemic models again. So these are similar to what you saw in lecture 2.10. But of course instead of using difference equations we're going to be using differential equations instead. So let's go ahead and list other objectives, which are going to be very similar to what we did the last time we talked about epidemics. The first objective is to apply differential equations to modeling epidemics. Second, we're going to understand how to construct a model. So we're going to be working with a number of different slightly varying compartmentalized models, and we're going to be getting differential equations, systems of differential equations from a set of assumptions. And lastly, we're going to see a couple of the things that can go wrong with modeling. During analysis, as well as applying some of the real-world facts to constrain what the model does. So, assumption 1, we're going to go ahead and start building up epidemic assumptions. So, let's start with the very basic one. Each infected individual infects other individuals. This is required for epidemics. So each infected individual infects others at a rate beta. Okay, so this gives us our first super simple model of epidemics, which is going to have a number of issues, but let's start with it and see what happens. So each infected individual infects others at some rate beta. That means the rate of change of the number of infected individuals is proportional to the number of infected individuals. So this is going to give us a set of just a single differential equation, di dt is equal to beta times I, where I of t is equal to the number of infected individuals. At time t. Well, this is just a simple linear first order differential equation, so we know how to solve this. So let's rewrite this. This is I dot minus beta I is equal to 0, and let's use the characteristic equation, though we can of course also use integrating factors. So characteristic equation is lambda minus beta is equal to 0, which implies that lambda is equal to beta. That gives us an ansatz for the solution form, which is I of t is equal to some c times e to the beta t. And by substituting in t equal to 0, you get that I of t is equal to the initial number, I of 0, times e to the beta t, assuming time starts at 0, of course. So this is just exponential growth. Now, of course, this model has some problems. The biggest one is that this will grow exponentially to infinity, and that's not really realistic because there are a limited number of potential hosts. So this model might work early on in the epidemic, but it really fails once people start getting more infected and you start getting some leveling out of the infection curve. So this is the exponential growth model, and it has the shortcoming of fails to consider limited population size. So let's go ahead and add a second assumption, assumption 2. There is a total fixed population size We're only going to work with fixed population size models in today's lecture just because things get a little bit more complicated when you have when the population size can change. But of course, in general, the population size isn't a fixed number. You can think of this as approximating the case when the epidemic spreads really quickly, and so the population isn't actually varying that much over the course of the epidemic. And where n is equal to some I of t plus s of t, where s is the number of susceptible individuals. And of course, let's go ahead and modify assumption 1. And instead of the infection rate being just beta, the infection rate, well, we want it to be proportional to both beta and the fraction of uninfected, of susceptible individuals. So the infection rate is proportional to beta and to the fraction S over n of susceptible. Basically, when an infected individual comes across another infected individual, well, an infection won't happen because both parties are already infected, and so you only really are counting the fraction of encounters where you're talking to someone who is susceptible and might be infected. Now, this leads us to our first compartmentalized model for this, and this is going to be called the SI model. And we're going to have two compartments. We're going to have S, and we're going to have I. So, and what's this rate? Well, it's proportional to the infection rate is proportional to beta, and it's proportional to the fraction. Yeah, so it's going to be proportional to beta, and it's going to be proportional to S, and it's going to be proportional to I and n. So we're going to write this as beta I n because what we're saying in writing out this compartmentalized model, we're saying that for every one of the individuals in S, we have this rate going from S to I of beta I over n. So note that there is an implicit I here. Or sorry, there's an implicit S here, but we're going to treat that as implicit for compartmentalized models today. Just make sure that you're consistent about whether you include that term in your diagram. Okay, so what does this look like? So we still have n is equal to s of t plus I of t. And we have s dot, where s dot is ds dt of t. I'm not going to write out the of t's, and they're just going to be implicit for notational simplicity. So this is going to be minus beta s over beta si over n, and I dot is going to be equal to beta si over n. And we can combine all these things together. So note that this implies that s is equal to n minus I. So I dot is equal to beta over n times n minus I times I. And we can rewrite that. So I dot is equal to, let me write this in several different colors. Beta I times 1 minus I over n. And this is some function f of I, because everything else is a constant there. Now, the first thing we want to do is we want to figure out what the equilibria of the system are. So this is just a logistic so some of you may have noticed that this is just logistic growth. And so it is possible to explicitly solve this, but we're going to just solve this qualitatively using a phase line. But the first thing we need to do is we need to find the equilibria. And we have I bar is equal to either 0 or n, which you can see pretty easily by looking at the two different pieces. Now, when we're drawing out a phase line, well, what do we get? we have a phase line, and we have our 0 equilibrium here, and we have our n equilibrium here. You could use the first derivative test to see if they're locally asymptotically stable, but because we can use a phase line since this is a 1D system, we actually can get global asymptotic stability by just looking at the directions of the arrows on this phase line. So in this corner here, down here, we know that f of I is equal to a negative number because here I is, this is the I axis. So below, when I is less than 0, well then beta I, a player, is going to be less than 0, times, well, when I is less than 0, well that means 1 minus I over n is going to be positive. So this is less than 0 if I is less than 0. Well, let's consider the case in this region. So we have f of I, which is equal to, well, I is positive, so beta I is also going to be positive. And 1 minus I over n, well, I is between 0 and n, so I is less than n positive, so I over n is less than 1, so 1 minus I over n is then still positive. And so this is greater than 0 if I is greater than 0 and less than n. And lastly, we have over here let f of I is equal to, well, I is still positive, but now because I is bigger than n, I over n is greater than 1, so 1 minus I over n is now negative, which is less than 0 if I is greater than n. Okay, so we can draw these out. So what we end up with is an arrow pointing this way, an arrow pointing this way, and an arrow pointing that way. Therefore, we know that this here, this is globally asymptotically stable. Which, of course, we already, well, for the starting point I of 0 is greater than 0. For any if there is any infected individual, well, with this simple model, you're going to go up to the point where all individuals are infected because no one ever recovers or dies because we're not working with births and deaths in this model. And one other thing to keep in mind is we don't care about negative I because you can't let me actually write that a little bit more cleanly. So this case, irrelevant because it is not physical to have negative infected individuals. Okay, so that's our simplest model of pandemic, and this is basically the pandemic where no one ever recovers, which is bad, but luckily people do recover. So if we want to model that, we need to introduce an additional assumption. So this is going to be assumption 3. Individuals recover at some rate gamma, but become susceptible again. So they recover, but they don't become immune. So this is known as the SIS model. And again, we have our two compartments, S and I. And this rate here is still beta I over n, because for every susceptible individual, they have a beta I over n chance of becoming infected. And we have another arrow gamma going back now. So when we write this out, and we're assuming constant population size though, so n is equal to s of t plus I of t, and we have s dot, so ds dt is equal to minus beta I of, let me rewrite this because this will beta over n I times s, let's say s times I plus gamma I, and I dot, well, that is equal to beta over n si minus gamma I. And we know that s is equal to n minus I, and so we can substitute that in. So we get I dot is equal to beta over n times n minus I minus gamma I. And therefore I dot is equal to beta minus beta I over n minus gamma times I. So it's basically factoring out the I onto the right-hand side. And now we have a couple different cases here. So the first case is where beta is equal to gamma. Well, when I dot is equal to minus beta over n I squared, because the beta and the gamma cancel out, they're equal 0, and I bar is equal to 0. Okay, so what does this look like? Well, we have our phase line here. We only have one equilibrium, 0. And you'll notice that no matter what I is, I squared is, so long as I is not equal to 0, I squared is positive. And beta and n are both positive as well, so you get a minus sign on both. So both above and below 0, you go in this direction, and therefore, and 0 is globally asymptotically stable for I of 0 greater than or equal to 0. Note that, of course, don't care about this area. Okay, so that was the easiest case. Case 2, well, we have beta is not equal to gamma. Well, then what we can do is then we can divide out by beta minus gamma. So then we get that I dot is equal to, well, let's divide out by beta minus gamma, and I'm going to write this in different colors because we're going to, again, do the sign analysis we did a moment ago. So beta minus gamma, let's have an I here, and let's use orange for last part, which is 1 minus beta over beta minus gamma n times I. Okay, so what we did there is we took the stuff in the parentheses up here and divided out by beta minus gamma. So you're going to get 1 minus beta I over n times beta minus gamma, and we move that out in front. And, well, let's compute the equilibria. So then we know that I bar is going to be equal to 0, or it's going to be equal to beta minus gamma over beta times n. Okay? So that's just setting it equal to 0, because we know that beta is not equal to gamma, and so therefore the blue term can't be equal to 0. And of course, you do also get, since this is a system, you do also get then that S bar is equal to n or gamma n over beta. But it doesn't really matter because S is completely determined by I. So now let's consider the different cases again. So let's consider case 2a, which is going to be where beta is less than gamma. Well, then if beta is less than gamma, 0 is the only positive equilibrium. Because again, we don't care about when it's negative. So we end up with a phase line that looks something like this. So we have our 0, and we have our, let's see, this is beta minus gamma n over beta. But we don't care about, this is all irrelevant. And we know that in this region, we have f of I, or let's say this is f of I. F of I is equal to, well, beta minus gamma is negative because beta is less than gamma, times, well, I is positive. And since I is positive, we end up getting that a moment. Oh yeah, so we end up getting I is positive, but beta minus gamma is negative, and so therefore this entire term up here, is negative, and then you subtract that, so that's positive, and so you end up getting a positive number there. And so that is less than 0. If I is greater than 0, and so therefore these arrows point inward. And together this implies that 0 is globally stable for I of 0 is greater than 0. And we don't care about anything with negative, where it's negative. Of course, now we also have a case 2b, which is where beta is greater than gamma. Then both of our equilibria, I bar are equal 0 and I bar is equal to beta minus gamma over beta times n are positive. So we do need to consider more case analyses. Well, let's write this out. So we have the case of 0 here, and let's say this is beta minus gamma divided by beta, divided by beta times n. And so let's start by classifying. So again, this is irrelevant. We don't care about that. And let's see what's going on here. So in this range, we have f of I. Let me, yeah, you guys can see both. So here we have f of I is equal to, well, if I is between these two numbers, well, beta minus gamma is always going to be positive. I is always going to be positive, and this is true for both this range and the range when it's greater than that. So these are both positive. But now, of course, we're left with the orange term. And the orange term is going to be positive when it's less than beta minus gamma n over beta, because then what happens is this entire quantity up here is going to be less than 1, and so 1 minus something that's less than 1 is going to be positive. On the other hand, when it gets big enough, it's then going to be negative. And so this is greater than 0, and this is less than 0. And so we end up with an arrow this way and an arrow that way. And because we end up with those arrows, this implies that unless I bar is equal to this positive equilibrium, beta minus gamma over beta times n, is globally asymptotically stable for I of 0 greater than 0. And it turns out that we can define a quantity R naught, which we've defined before in other lectures. R naught is equal to beta over gamma is the basic reproduction number. Basic reproduction number of the system because it is the number of secondary infections beta caused during the infectious period infectious period 1 over gamma, because you're recovering at a rate of gamma. And when R naught is greater than 0, is greater than 1, implies that the disease persists. R naught is greater than 1 implies that beta is greater than gamma, which is the case 2b, which this is known as the endemic case, because the disease does not die out. So disease persists. When R naught is less than 1, this implies that beta is less than gamma, which implies we're in case 2a, in which case the disease dies out and you get a disease-free equilibrium. Disease-free equilibrium. Disease dies out. Okay, so that was a relatively simple analysis for the case where you only had these two compartments. And when you only have two compartments, you can just go ahead and use the phase line, and that's really easy to understand global stability because you just need to draw arrows and point a lot of the directions that the trajectories move along their line, and you can't have any periodicity, and so you're a safe flare. Now, unfortunately, we often care about more complex models. And so let's go ahead and modify assumption 3, and let's introduce immunity into the equation. Ideally, when you're infected and you recover, you become immune instead of just becoming susceptible again. And so let's model that. This is modified assumption 3. Individuals recover at rate gamma. Recover at rate gamma and become immune. And we're going to call this removed from the population, i.e. no longer susceptible or infectious. And this brings us to one of the classic models, which we covered in the difference equation setting, but this is the SIR model. SIR model for susceptible, infected, removed. We have 3 compartments, and this is one of the classics of the field of epidemiology. So we have the S model, S compartment, we have the I compartment, and we have the R compartment. And the rates here, let's just keep the rates from before. So beta I over N. And here we have gamma. And so we can write this as a system of differential equations. We get N is equal to S plus I plus R. And these are all functions of t. And we get S dot is equal to minus beta over N Si. We get I dot is equal to beta over N Si minus gamma I, which we can rewrite, and this will be helpful a little bit, as I beta N S minus gamma. And we have R dot is going to be equal to gamma I, because that's the rate at which individuals become recovered. So we have the system of equations, and of course we can simplify it a bit into a system of 2 equations because we know we have the constant population assumption. So we know that R is equal to N minus S minus I. So can consider just S and I. So we're left with just S dot is equal to minus beta N Si, and I dot is equal to beta over N Si minus, actually let me write this the way, by I times beta over N S minus gamma. But since this is a 2-dimensional system of equations, we can't use a phase line, we have to use a phase portrait instead. So let's start by talking about the Noke lines. So let's say we have an S Noke line. So this is the set of points where S dot is equal to 0. So S dot is equal to 0 is equal to minus beta N Si, which implies that I is equal to 0 or S is equal to 0. And we also have an I Noke line. So this is when I dot is equal to 0. And I dot is equal to 0 is equal to I times beta over n s minus gamma. And this is the reason we factored it out, because this implies that either I is equal to 0, or we know that s is equal to n over beta times gamma, for the second half to be equal to 0. And of course, the equilibria are just the intersection points of these two no-plines. So the equilibria, well, when do these intersect? It turns out that the intersections are just whenever I is equal to 0. So this is I bar is equal to 0, and S bar is just any real number. And we can see this. So let's draw this out. And I'm going to draw this out in two different cases. So case 1, I'm going to say that gamma is less than beta. Gamma is less than beta. We're only going to care about the positive quadrant, since we don't care about anything left negative. And we have our S-nocline. So our S-nocline is just when I is equal to 0 or S is equal to 0. And we have our I-nocline when I is equal to 0. So when I is equal to 0. Or when S is equal to n beta times gamma. And note that, of course, the intersection of these two noclines is the equilibria, and so let's just, this I bar is equal to 0. So all of that is equilibria. Let's say this point here is n gamma over beta. And this point here is 0, the origin. Okay. Now, one of the other facts that we know is we also know that S plus I has to be less than n, because S plus I plus R is equal to n, and they're all positive numbers. Therefore, we can also draw another line here. So this is the, let me point the arrow the other way. This is the S plus I equal to n line, and we know that we have to be underneath it because it has to be less than n. So now what we want to do is we want to analyze all the different directions along the noclines. So let's see. Let's do this explicitly. If if S is equal to 0, so on the S-nocline, if S is equal to 0, well, then I dot is equal to some value of I, so is some positive value. So a positive value times, well, beta n S minus gamma. Oh, wait a moment. What did I do wrong here? So if S is equal to 0, then we know that S dot is going to be equal to 0, and I dot is going to be a positive number times, give me a moment. We know that it's a positive number, and S is equal to 0, so that's going to be minus gamma as the second number there. So this is going to be times a negative number, which is less than 0. And therefore, the arrows point downward along the I-axis, so when S is equal to 0. We also have that if S is equal to n gamma over beta, so along the I-nocline, we know that S dot is going to be equal to, well, we have S is positive, I is positive, so this is going to be a negative number times a positive number, which is less than 0, and so we end up with these arrows. And lastly, you can, of course, extend this analysis. So it turns out that if S is less than n gamma over beta, we know that I dot is less than 0. And we know that S dot is less than 0. And if S is greater than n gamma over beta, then we know that I dot is greater than 0, but S dot is still less than 0. And so what we end up with is these arrows. Oh, sorry, that's the wrong way. And this is our phase portrait. And so there are a couple things to note. Note, if S of 0 is greater than, so if our starting point is greater than n gamma over beta, when infections increase to a maximum at S is equal to n gamma over beta, because everything's moving to the left, of course, and you can't change direction to go downward until you cross the NOC line before decreasing. So the epidemic happens. On the other hand, if S of 0 is less than n gamma over beta, then infections just die out to 0 at some point on the x-axis, the s-axis. We don't know exactly where it dies out to, because that depends on exactly how many people were infected to begin with, or sorry, how many people were susceptible to begin with. But regardless, the infections just die out because you're in this regime here. Okay, so that was, now you might be wondering, how would you start out with some individuals who are already, how would you start out with some fewer individuals susceptible than the total? And that can happen if you previously had an epidemic, and the second epidemic happens when you still have herd immunity, basically. But now let's consider the other case. So that's the case when gamma is less than beta, and so basically when the recovery rate is less than the infection rate, you can have an epidemic. What happens when gamma is greater than beta? Well, then we'll pretty easily show that you cannot have an epidemic ever. So what happens then is you can do the same analysis, and we're not going to write all of it out again. What you'll find is that the NOC lines are as before, except the difference here is that the NOC line here, so this is the n gamma over beta NOC line, is outside of the feasible range. So note that you can't have more individuals, you can't ever be in that region of the phase space because n plus n has to be equal to s plus I plus r, and so s plus I have to be less than n. And so you're entirely in this regime, and therefore because S of 0 is always less than or equal to n is less than n gamma over beta, infections just die out and don't cause an epidemic. So it turns out that in this particular case, R naught is going to be equal to beta over gamma, is the basic reproduction number again. And it determines if an epidemic is possible. So when R naught is less than 1, an epidemic just isn't possible, no matter if everyone is still susceptible. Whereas when R naught is greater than 1, then an epidemic is possible, especially if you start out with most people being susceptible, which you would expect if it's a new disease. Okay, so now we've seen a couple different examples. I'm going to leave you with, so we saw the Well, basically just we saw the SI model, we saw the SIS model, we saw the SIR model, and I'm going to leave you with another example that we're going to look at a little bit more carefully in the in-class exercises. So this is going to be the SIRS model. So let's give another assumption, and so we can discuss that. So this is assumption 4. And this is if recovered individuals lose immunity. Immunity at rate, let's call it nu. So this is what happens whenever, maybe after you get some disease, for example, maybe you get some fancy new coronavirus that infects you. After you recover from it, you're immune for a while, but maybe you lose your natural immunity over time. In that case, you can't eventually get the disease a second time after some amount of time has passed. And so this would be called the SIRS model. And again, we have our standard 3 compartments, S, I, and R. And we have our usual rates. So this is beta I over N. This here is gamma. And this here is nu. And this has a different set of equilibria. And of course, you can still use a phase plane analysis, but let's go ahead and write out the equations. So we have S dot is equal to minus beta over N Si plus nu R, because we get some amount of recovered individuals turning into susceptible individuals. We have I dot is equal to beta over N Si minus gamma I. And we have R dot is equal to gamma I minus nu R. And we'll still be in a constant population size assumption. This will not always be the case, so you may have models where your population size can change over time. So even though these are functions of t, n is not a function of t. R is equal to n minus s plus I. So can substitute to get a system of 2 equations. And so what we're left with is just S dot is equal to minus beta over N times Si plus nu times N minus S minus I, because that's what R is. And we get I dot is equal to I times beta over N S plus, minus nu. No, sorry, that's not a nu. That should be a gamma, minus gamma. And this will be exercise 6.15 in your homework. 6.15, which is basically use a phase plane analysis to determine equilibria and stability. What is R naught in this model? Okay, so I think that's where I'll leave off. But just in conclusion, we've learned a lot of techniques for understanding model dynamical systems using differential equation models. And in today's lecture, we applied all of this knowledge to understanding a different set of epidemic models based on different starting assumptions. And of course, for every single starting assumption, your model changes slightly, and your analysis and the asymptotic behavior also changes. But we have lots of different tools to allow us to understand those behaviors. Thank you very much, and I will see you in class.